Once again, can you hear my voice clearly? Boleh?
Yes, sir.
All right, good. Thank you very much. Thank you for your response. All right. So tonight we will continue our lessons on solid on this what we call the as a solid and fluids. Okay, we have discussed this morning or this evening. We have discussed about Archimedes principle. Okay, the Archimedes principle that takes the difference in the pressure, okay, the upper side and the lower sides of the pressure if we put the object on the fluids or in the fluids. For instance, we have a object in fluids, so there should be the difference in the pressure of the lower side and the upper side that we can count as the buoyant force. Okay, so there should be a partial a fully submerged object and also a partially submerged object. So we have done the examples. We have done at least three or two examples regarding Archimedes principle. Okay, Archimedes principle done. So that is the first subtopic, subtopic for chapter 9. Okay, now we will continue on the second subtopic of the chapter 9. Way back goes to the slide number 63, the deformation of solid. The deformation of solid. Please go to the slide. Okay, let me share the slide. Okay, so this is the slide of the deformation of solid. Okay, right. Okay, so first of all, the words deformations of solid means that we need to do something to the solids. Okay, as you can remember, in our very first slide of a solid, you can see the arrangement of atom. Okay, arrangement of atom which is slightly close, atom is close towards each others, and there should be some sort like spring, okay, in between those atoms. Okay, that is what we call as interatomic, or should I say that interatomic change between the atoms. Okay, so what we can do is for to deform the word formation. It is a deformation means that it's the counter for formation. Formation ialah pembentukan. So deformation means that it is how the solids can be uh, adjust or can be turned into something else. Not really turn or not really change, but we can see in terms of a certain properties. Okay, so the elastic properties of solid are discussed in terms of stress and strain. Okay, so stress is the force per unit area, as you can see, force per unit area. So when you took force per unit area is equivalent to stress. Okay, we have force per unit area that is similar to pressure. Okay, because pressure is also force per unit area. Okay, so meaning that if I said that stress, okay, it also equals to pressure, right? But in terms of deformations of solid, in terms of how can we alter the solid, mengubah, so it cause when you apply some stress, you apply some force in the base in the some area, it's actually causing some deformation. It actually change a little bit properties of solid. Okay, change what we call that something's related to length, area, and also volume. So we might see that a little bit change in that solid is what we call as solid deformations. Okay, so the deformations of the solid, or the change change in the solid itself is what we call as strain. Okay, you have stress and you have strain, meaning that strain is what? A measure of the amount of the deformations. That means how much, okay, solid is changed. So that is equivalent to strain. That means stress is you apply, strain is you get it. What you apply, you get it. So stress and strain, yeah, it is related to each other. Okay, for sufficiently small stresses, stress is proportional to strain with a constant proportionality depending on the material being deformed and on the nature of the deformation. We call this proportionality constant as the elastic modulus. So, the modulus, or some also we call that as constant value, or how can we connect between stress and strain, is using the word elastic modulus. Okay, as I said to you, elastic is the properties of the material that make some adjustment. If you want to adjust something, that it should turn to it wants to turn to the urge to turn to the original position. That is what we call as elastic behavior. So in this case, we use elastic modulus. So the elastic modulus is what? Okay, the word elastic modulus is an analogous to a spring constant. Okay, like spring constant K. You can think of it as a stiffness of a material, that a material having a large elastic modulus. Okay, that means if the larger the elastic modulus, that means the material is very stiff, sangat keras. Okay, very stiff, cannot be agile, cannot easily deform. Okay, so it very stiff and difficult to form. All right, again, stress is a force per unit area, while strain is the outcome from stress. That means the measure of amount of the deformations. Okay, there are three relationships having the form of the equation shown, corresponding to tensile, shear, and bulk deformation. As I can see here, is you have a tensile. Okay, okay, we have a tensile, we have shear, and we have bulk deformations. So what is tensile, shear, and bulk? There are three of them, right? So now we can see the difference between all of them. Okay, and all of them satisfy an equation similar to Hooke's laws for springs, which is F equals to negative kx, where F is the applied force, okay, and K is the spring constant, right? And delta X is essentially the amount by which the spring is stretched or compressed. So now you can see that, okay, the relationship between stress, strain, and elastic modulus is given by this equation, which is stress is equivalent to elastic modulus times strain. Or I can put it that way, the elastic modulus is the ratio between stress over strain. Okay, elastic modulus is the ratio between stress and strain. Okay, let's go to the other parts. Now, first of all, we call it as Young modulus. That means the elasticity in length. Okay, so to consider the Young modulus, we need to see some elasticity towards the length. Okay, in first we need to see a tensile stress. So what is the tensile stress? So it is the ratio of the magnitude of the external force to the cross-sectional area. Okay, so meaning that if you look carefully to this part, where you can see that this is the original length of L naught. So this is the original length. And then when you apply some forces towards this cross-sectional area, so this is the area, cross-sectional area of the some material. So it costs you some delta L. That means we can see the solid have deformed and changed with the additions of delta L, additions of delta L. Okay, does it influenced by anything? No, but through the force. That means the force per unit area given by, uh, I don't know, maybe us. Okay, it's what we call as stress. Okay, so in this word we can see the word tensile has the same root as the tension. It is used because the bar is under tension. Okay, so the tensile strain is the case is defined as the ratio of the change in delta L to the original length of L naught, and it is therefore a dimensionally quantity, a dimensionless quantity. That means it doesn't have any quantity. Okay. So we can write an equations relating tensile stress to tensile strain, where Y is the constant proportionality called Young modulus. Okay, so again, I would like to remind you. So we have some elastic modulus. Remember, we have stress is equivalent to elastic modulus times strain. So therefore, F over A is considered to be stress, and delta L over L naught should be your strain, and the Y here is what we call as elastic modulus. So in this case, when you apply some force towards some area for the length, so it gives you Young modulus. This is what we call as Young modulus. Okay, now we have three. Okay, now it's number one, which is Young modulus. That means you apply a force to a certain area, then it consider to change or from the original length some delta L. Okay, and then of course the unit will be Pascal. Okay, the SI unit for stress will be Newton per meter square, or called Pascal. Okay, so that is number one, which is Young modulus. Now we go to the something that we call as shape table shows some typical values for Young modulus. Okay, a material having a large modulus is difficult to, okay, to stretch or compress. Okay, quite a value here. You can see okay, you compare it to the from aluminium that have 7 times 10 power of 10 Pascal, and try to compare it with the rubber, for instance. The rubber at 0.1 10 power of 7. So the larger the value of Young modulus, that means the stiffness is high. Okay, so you can now see this, the experiment shows that the change in length for a fixed external force is proportional to the original length, and the force necessary to produce a given strain is proportional to the cross-sectional area. So the value of Young modulus for a given material depends on whether the material is stretched or compressed. Okay, it's either stretched or compressed, regardless of maybe not just addition, but if you can make the delta L change, okay, sorry, you can make the original like this one, okay, the original line L not change to at the certain delta L, so you can have some stress, and of course it costs you strain. Okay, now we go to the next part here. This is a very popular, or a very or not powerful, but it's actually very well known stress and strain graph. Okay, when you say that you have a stress in y-axis and strain on the x-axis, and of course, as the modulus, okay, these are the elastic modulus. That means uh, is it possible to exceed the elastic limit of a substance by applying, okay, a sufficiently great stress, as you can see in the graph, and at the elastic limit, the stress strain curve is no longer a straight line. Okay, you can see here at the elastic limit. Okay, what we call that as elastic. That means at a certain stress, that means let's say 200 Pascal, megapascal. So it behave like a normal strain, which is uh, it increase directly proportional to the stress. Okay, strain increase and directly proportional to stress. But until it reach the elastic limit, okay, what will happen at the elastic limit? Okay, the stress strain curve is no longer a straight line. Okay, it doesn't go this way, but it goes a little bit flat. Okay, no longer a straight line. A material subjected, okay, to a stress beyond this limit ordinarily doesn't return to its original length when the external force is removed. So as you can see, when you have material, okay, there should be, or there should have, okay, every material should at least have some elastic modulus behavior, or elastic properties of the material. For example, if we have socks, okay, getah pada stocking, okay, socks, and until it reach the elastic limit, okay, until it reach the elastic limit, okay, the socks, okay, if you try to, okay, make the socks become, or try to stretch the socks, okay, the socks still can return to its original position, but until it reach the elastic limit, after that, what will happen is the sock cannot go back to its original position or original shape. And in fact, okay, at some point, as the stress is increased further, it surpasses ultimate strength. Okay, the greatest stress the substance can withstand without breaking. So that means it can go until a breaking point. After that, what will happen for ductile material? Like copper or gold. Ductile ni maksud dia like a metal. Okay, boleh dibengkokkan. Bengkokkan like metal, besi. Okay, kayu is not ductile, not really ductile, but mostly besi lah, besi metal. For ductile material like copper, gold, after passing ultimate strength, the metal thins. Okay, if we try to put the stress anymore, kita boleh bayangkan kalau kita ada satu machine, kita cuba tarik apa panggil, tarik besi, dia lama-lama dia akan jadi thin, okay, jadi nipis, and finally after a certain level ia akan putus, ia akan break. And this is very very high value of stress and strain. Okay, bukan kita main tarik sendiri je, bukan macam tu. Right, that's what we call ductile material. But for brittle material, okay, of course dalam material ni ada ductile, ada brittle. Okay, ductile lah macam tu lah. Kalau brittle pula macam more kepada, kalau kita cuba nak break dia, dia akan terus patah. Okay, so meaning that the breaking point is not as high as a ductile material. Okay, okay. So it's very good to understand. Okay, look at the use of stress and strain. Now we go to the shear modulus. Okay, what is shear modulus? Okay, another type of deformations occurs when an object is subjected to a force F. Okay, look here. Subjected to a force F parallel to one of its faces. This is the face. Okay, and then of course this is another face. All right, and then of course when you apply some forces, okay, what falls under shear modulus? Okay, again, when you apply a Young modulus, for instance, we apply a force towards the area. That means force perpendicular to the area. Okay, force perpendicular to the area, and we only uh, put a stress on a certain directions only. There's only one directions. Okay, hanya ada satu satu apa bagi satu arah saja force. But when you talk about shear modulus, it's actually a deformation occur to an object for the force that parallel to one of its faces while the opposite face is held fixed by a second force, as you can see in the figure on the left. So senang cerita, kalau kita nak tengok macam mana, kita tengok macam ni. Yes, ada buku tebal kan, kita tolak dia. So one of the force is going to the right, and the some things that going to the left, okay, have made the book to become, if I can write, okay, normally book is dalam pandangan depan macam ni, tapi when you pull one force to this side and the other force on this side, Okay, that is a static friction, for example, it becomes like this. Okay, so this book, dalam pandangan sini, dalam pandangan depan sini, so this book is considered to have a shear modulus. That means you apply some force, okay, you apply some force, and it gives you some area. Okay, it gives you in the some area, so it gives you some uh, problem to that. Okay, it gives you some strain. So there is no change in volume with this kind of deformation. Remember that in the shear stress, the applied force is parallel to the cross-sectional area. And tensile stress is the force is perpendicular to the cross-sectional area. So the equation should be like this one. Okay. Yeah. We define the shear stress as F over E. Okay, force per unit area, again, that is the shear stress, and the ratio of the magnitude of the parallel force to the area of the face being shear. Okay, the shear strain is the ratio of delta X over H. Okay, a delta S over H, where delta X is the horizontal distance in the shear faces move, and H is the height of the object. Therefore, it should be like this. Okay, the equation F over E will be based on S and delta X over H. Okay, so delta X is the horizontal distance, where H is the height of the objects. So the shear stress is related to the shear strain according to the equation shown here. Okay, where S is the shear modulus. So this S is what we call as shear modulus. Okay, and of course the shear modulus with the unit of Pascal. Every elastic modulus comes with the Pascal. That means it's a ratio between stress and also strain. Okay, so here are some shear moduli. That means more than one shear modulus for some material are listed in the table. Okay, you can see here. Okay, all aluminium, all the substances from Young modulus can be written down in shear modulus. Okay, but that is, of course, uh, that you should define Young and shear modulus. Okay, because this is not the same modulus. Okay, Young comes from the force acting on the cross-sectional area, while force that goes face to face, and one of the forces going the other way from the other force. So that is what that is cause some shear modulus. That means it reflects to the area. Delta X over H, okay, is the strain. So this is stress, this is modulus, the shear modulus, and delta X over H is considered to be shear stress. Sorry, shear strain. Okay, now we go to the bulk modulus, the third one. Okay, the volume stress. Okay, now we have, okay, you can see in the slide, or you can see we have some a solid cube that is under a uniform pressure and is therefore compressed or on all sides. On all sides, you can see here. Okay, it compressed at all sides. Okay, this is the cube. Okay, the cube, that means it should have six faces. Okay, six faces, ada 6 muka. 1, 2, 3, 4, 5 dan 6. Okay, and what we call that, and then they have been compressed at a certain value. Okay, compressed, that means you have given some pressure at all sides of the sides. Okay, so the arrowheads of the force vectors on the sides of the cube that are not visible are hidden by the cube. So of course there should be at this side. Okay, belah belakang tu ada, belah bawah ada, belah tepi ada, kiri kanan. Okay, so the bulk modulus characterize the response of a substance to a uniform squeezing. Okay, imagine that the external force acting on an object are all perpendicular to the surface on which the force acts and are distributed uniformly over the surface of the object. Okay, and of course shown in the figure. This occurs when an object is immersed in a fluid. An object subject to this type of deformation undergoes a change in volume. So this is the one I want to emphasize. We have discussed about Young modulus, and it is about length. Okay, that means you apply some stress. You can see all this at the all stress level F equals to A. That means you apply some stress, it give you elastic modulus. So the elastic modulus for the Young is Y, which is we call that as Young modulus, and times with strain, the tensile strain. Okay, which means delta L over L naught. Change in length over original length. So that is for Young modulus. For Buck modulus, sorry, for shear modulus, we have F over A, which is the stress, times with shear modulus times shear stress, shear strain, which is delta X over height of the object. Okay, delta X over height of the object. Because when you multiply height of the object times with the delta X, so you may find some area. Okay, that is due to the area. And here, okay, um, we call that as the stress. We apply stress to the volume of the object. The volume of the object. So the volume stress is defined as the ratio of the change in the magnitude of the applied force delta F to the surface area. From the definitions of pressure, delta P here, okay, is also simply a change in pressure. Okay, so why not we just use F over A? Okay, because it's not a matter of force over area anymore, because it gives you a pressure. Of course, I know force per unit area is pressure, but the delta pressure is the change in the pressure. So the changing of pressure give you some change in volume. So the volume strain is equal to the change in delta V divided by the original V. So we can relate a volume stress to a volume strain by the formula. Show delta P equals to negative B over times with delta V over V. So this is the only solid deformation is the only the contain the only negative in this case, because the negative sign is what? Okay, so a material having a large bulk modulus doesn't compress easily. So therefore, the negative sign is included in this defining equation so that B is always positive. An increase in pressure for positive, for example, a positive delta P causes a decrease in volume and vice versa. Okay. So now we take the examples, but we'll go to the volume elasticity first, which is we have a delta, so a delta P equivalent to negative B delta V over original V. And of course, B is what we call as Buck modulus. Okay, and of course we can see it. We have a Buck modulus. Okay, there's all substance from the aluminum until mercury. There's a few substance that it doesn't have a Buck modulus. Okay, so let's look at the examples. We look at the examples first. Okay, a vertical steel beam in a building supports a load of 6 times 10 power of 4 Newton. So this should be your force. Okay, if the length of the beam is 4 meters and its cross-sectional area is, yes, this one should be your A. Find the distance the beam is compressed along its length. Okay, try to imagine that. Okay, this all the deformations, of course, you can see you can apply a force, and then you can see you can apply some stress, and you can see the strain. But the strain is not really um, appear to be visible enough because it's actually changed a little bit only. Okay, as you can see here, when you put the value all together, and from the calculation, we want to find the delta L, obviously, and then we put it, we rearrange the equation so that F over A, okay, you pull the Young modulus because it's used steel beam, so always uh, refer to the list I've given in the table. What is steel? What is Young modulus for steel? So it's stated here as 2 times 10 power of 11 Pascal, which is this one. Okay, you need to refer to the table, or in your final, for example, okay, you can refer to the question. Maybe it's given in the questions, right? So what is the delta L? So you can see from the calculation, you get 1.5 10 power of negative 4 meters. Okay, very small change, but a very significant one, which is 10 power of negative 4 meters. And then, what maximum load in newtons could the steel beam support before failing? So we need to apply, so we need to calculate the force given by F over A, which is F over A, F over 8 times 10 power of negative 3, which is F over A is equivalent to 5 times 10 to the power of 8 Pascal. That is for maximum load for before failing. Right? So find the maximum load that can support. See the compressive stress equal to the ultimate compressive strength from table 9.3. Yeah, we should refer to the table. So from here we can find the maximum load is equivalent to 4 times 10 power of 6 Newton. Right. So we go to the next example. Uh, defensive lineman of mass M at 125 kilogram makes a flying tackle at the initial speed of 4 meter per second on a stationary quarterback of mass 85 kilograms. And the linesman helmet makes a solid contact with the quarterback frame. Okay, so what is the speed of V final of the two athletes immediately after contact? So it's actually give you some approach in terms of dealing with the problems. For instance, okay, at the first part of this problems, okay, we need to apply some momentum. Okay, for instance, we have momentum initial equals to momentum final, and mv1 equals to m plus mvf, which is the when it collides between the helmet and also the femurs of the quarterback. So we can have a final velocity at 2.38 meter per second. And then at part B, if the collisions last for zero point 0.1, estimate the average force exerted on the quarterback's femur. Okay, that means you may apply some value here at uh, 0 to and force of certain value 2.03 force getting from the what we call it here. You need to refer to the table itself. Okay, to the table itself to get those kind of value, which is at 2.03 10 power of 3 newton. The shear stress for the helmet. And of course, the 5 times 10 power of negative 4 meters square as the area, cross-sectional area, like the one stated in this question. Okay, so you may find the shear stress, the maximum shear stress that can be held by the helmet, which is at 4.06 10 power of 6 Pascal. Okay, and this one I don't want to discuss it because it is not in your it is in the momentum, say impulse momentum. But the question now is, if the cross-sectional area of the quarterback is equal to the recalculate the shear stress exerted on the bone in the collisions. Okay, so we might want to calculate the cross-sectional area of that. Okay, first you need to calculate the speed of the final after the collisions, and then you can find the shear stress. Okay, from the shear stress, you can use that value to get the average force. Okay, in the questions. Right. So let's go to the examples. Next example using the buck stress. This one is for buck. Right. So ships and sailing vessel, okay, often carry lead ballast in a various forms, such as bricks, to keep the ship properly oriented and upright in the water. So basically lead ballast ini ialah apa yang ada pada kapal selam dan ada tangki dia tu. So normally ataupun ship lah dalam keadaan ni, kapal. Okay, dan the ship properly oriented in upright in the water. So bila ada bricks di sebelah tepi, dia tidak akan gelong macam melayang ke tepi, ke kiri, ke kanan, ya. Dia akan maintain straight throughout the journey in the water, right? Okay, so if suppose a ship takes on a cargo and the crew jettisons a total of 0.5 meter cube of the lead ballast into 2 kilometer deeps. Okay, calculate. Oh, sorry. Oh, tak dapat. Alright, no problem. I try to present from here. This one. Hold on. Okay, calculate a vertical. Sorry. What maximum? Number one, if the length of the beam is, this one is not the question. Sorry. Okay, this one, right? So number eight, calculate the change in the pressure at the depth, right? So first of all, you want to use some equations using rho Vg, which is rho is the density of 1.2 density given by here, the density of the seawater, because the ships akan take seawater, maka fluid dia ialah seawater. Okay, and the volume is given here as 2 kilometer deep. 2 kilometer deep ialah 2000 meters. Okay, you need to use 2 meters, and the volume. Okay, so and then G is 9.8, and the volume, then the weight of the ships is given by 2.01 times 10 to the power of 7 Newton. So that is the weight of the ship. First, the weight of the ships. Sebab nanti kita nak apply untuk dapatkan um, berapa force, okay, in terms of delta P yang kita akan calculate. Alright. Yang pertama ialah the change in the pressure at that depth. Okay, change in the pressure. So we know that pressure comes. Okay, pressure. Okay, now we have weight of the ships that is equivalent to the role of the fluid displaced. Okay, role of the fluid displaced. Maknanya kita dapatkan dulu mass of using the density of the seawater. Can refer to the table. Density of the seawater, and then volume of the seawater, which is at 2 kilometers deep, and then times G 9.8. So first kita dapatkan dulu weight of the fluid displaced at 2.01 10 power of 7. Yang pertama, itu bukan jawapan dia lagi. But the jawapan now is the change in the pressure at that depth. Okay, change in the pressure. Remember, when you want to apply some related to solid deformation, says number one, kita tengok dulu soalan dia. Kalau dia minta change in pressure at that depth and berkaitan dengan volume. So maksud dia ada kaitan dengan bulk modulus. So from this we get 2.01 divided by 1 meter square. So 1 meter square is what you get from the area, surface area. Okay. So that is equivalent to delta P equivalent to 2.01 10 power of 7 Pascal. Okay. 2.01 10 power of 7 Pascal. Okay, so as you can see here, this is the pressure difference between the surface and the depth of 2 kilometers is due to the weight of the water column. Okay, calculate the weight of water in column with cross section of 1 meter cube. Okay, is given by this uh, how they did the answers. So in the end, last one, the change in volume of the lead upon reaching the bottom. Okay, change in volume of the lead. So we can use lead. That means lead, okay, because it's made from lead, so you can refer to the table. The bulk modulus for the lead at 4.2 10 power of 10 Pascal. Then in the end, we will get delta V equals to negative 2.4 10 power of negative 4 meter cube. Okay, so that should be the examples for solid deformations. Okay, of course you can go through the slides, or you can go through the tutorial to find the examples. Okay, so that is the only subtopic for this chapter, the chapter 9. Okay, kita akan tutup dulu, stop sharing first. Okay. Rest of it kita dah tak masuk yes. Okay, kita dah tak ada dalam lesson plan kita. Kita hanya belajar Archimedes dan juga solid deformation. So kita dulu. Okay. Okay, kita boleh take a break dulu 1 minute. Okay, tak minum air ke apa ke. Okay, so let's continue on our next slide. Okay, next, please go to the next slide. Please go to the next topic. Okay, or next. So now we are in chapter 10. Okay, thermal physics. Okay, so everyone should see it. Nampak eh? This is thermal physics. Okay. So the learning outcome for this chapter will be the defined heat, temperature, and thermal equilibrium. Some of you may can see, for instance, number 3, convert the temperature scales between Celsius, Kelvin, and Fahrenheit. Okay? It's very easy to understand that. All right. Okay. So we start with the temperature and the zeroth law of the thermodynamics. Okay. What is the zeroth law of the thermodynamics? When we think about temperature, we generally think about how hot or cold an object feels when we touch it. So that is the degree of measure of hotness. But our senses can be misleading. A metal ice tray feels colder to the hand, for example, than a package of frozen vegetables at the same temperature, because the metals conduct thermal energy more rapidly than the cardboard package. So what we need is a reliable and reproducible method of making quantitative measurement that establish the relative hotness or coolness of object. So betul lah kalau kita pegang metal yang sejuk berbanding uh, vegetables yang sejuk, walaupun temperature dia sama, tapi kita akan rasa seolah-olah metal tu lagi sejuk. Tetapi in terms of degree, the measurement is the same. Okay. So a method related to solely a temperature is what we call as the hotness or coldness of object. So we as a scientist use a thermometer to understand or to measure the temperature. Okay, so when understanding the concept of temperature requires, okay, the thermal contact and the thermal equilibrium. These are the two, what we call that, two terms, which is thermal contact and thermal equilibrium. Okay, when two objects are in thermal contact, okay, ini nak faham zeroth law of thermodynamics. Okay, we have two objects that has a thermal contact. That means touch each other's, and if energy can be exchanged between them, and the two objects now are in thermal equilibrium. Okay, it means there should be some energy transfer from point A to point B and point B to point A, and then finally it reach some point where the energy cannot go back and forth anymore. Therefore, we call that as thermal equilibrium. Those uh, object A and object B are really in thermal equilibrium. Okay, because if there is no net exchange of energy. So heat is the exchange of energy between two objects due to the differences in their temperature. Right? Okay. So, so, so the zeroth law of the thermodynamics, okay, the summarize of it is the, or also known as the law of the equilibrium. If object A and B are separately in thermal equilibrium with third object C, then object A and object B are thermal equilibrium with each other. Okay, this statement is important because it makes it possible to define temperature. We can think of temperature as the property that determines whether or not an object is thermal equilibrium with other objects. Two objects are in thermal equilibrium with each other, maybe we are reach at the same temperature. So go back to this slide. When you have some thermal contact between object A and object B, so when there is no net change, so we are saying that when thermal contact happens, So no energy exchange between A and B. So we can say that between A and B, it reached the thermal equilibrium. Okay, reach the thermal equilibrium. And then, of course, when there is the object C comes to the object B, or for instance, okay, object C, that means a third object comes to this object C, and object C also reach the thermal equilibrium, we can say that A and C also have the thermal equilibrium. So that is what we call as the zeroth law of thermodynamics. So these are the schematic diagram of a mercury thermometer. Okay, normally we use temperature, we use thermometer, a mercury thermometer. Okay, because thermal expansion, the level of mercury rises as the temperature of the mercury change from zero, which is the ice point, to the 100 degrees Celsius, which is the boiling point. Okay, boiling point or the steam point. As we just discussed, thermometers are devices used to measure temperature. Okay, when thermometer is in thermal contact with the system, energy is exchanged until the thermometer and the system are in thermal equilibrium with each other. So that is how the thermometer function. All right, that means you put the thermometers, you can see that the mercury inside the thermometers have rise and reach to the same temperature or same coldness or hotness as you pour into the or in the water or in the fluids, or the one that you calculate the you want to measure the temperature. So that is given by the thermal equilibrium. So for accurate readings, the thermometer must be much smaller than the system so that the energy the thermometer gains or loses when it is in contact with the object doesn't significantly affect the energy content. Okay, a common thermometer you are all probably familiar with, it consists of mass of liquid, usually mercury or alcohol. Okay, that expands into a glass capillary tube when its temperature rises as shown in the figure. In this case, the physical property that changes in the volume of liquid, the change in volume of the liquid with the change of the temperature must be very nearly constant over temperature ranges of interest for the thermometer to be effective. So what I'm telling you is the thermometer and the temperature are related because when you want to measure a temperature, okay, we use a thermometers that use some in the system of zeroth law of thermodynamics. Okay, you can see here in the left figure, this one, a constant volume gas thermometer measure the pressure of the gas from here. Okay, measure from the pressure of the gas contained in the flask immersed in the bath. Okay, flask immersed in the bath. So on the right, you can see a typical graph of pressure versus temperature taken with a constant volume gas thermometer. Okay, so from this thermometer, we can plot a pressure versus temperature. Okay, as you can see, the pressure at the freezing point of water, which is at a certain value, and the pressure at the boiling point of the water at around 100 degree Celsius. So the thermometer we just discussed can measure the temperature, but it doesn't define um, temperature in the fundamental way. One type of thermometer is more fundamental and gives us a way to define temperature and relate to directly to the internal energy. Okay, but this one is very important. The constant volume gas thermometer and the Kelvin scale. Okay, this should be the graph of pressure versus temperature. Okay, pressure versus temperature for experimental trials in which gases have different pressure in a constant volume gas thermometer. Okay, we have a first trial, a second trial, and the third trial. That means you uh, have get some experiment shows from the thermometer readings made with a gas thermometer, that the one that I showed you just now, containing different gases nearly okay, independent of the type of the gas used, as long as the gas pressure is low and the temperature is well above the point at which the gas liquefies. Okay, we can also perform the temperature measurements with the gas in the flask at different starting pressure at 0 degrees Celsius. So it states that at a certain zero, okay, you can see that from all the trials, when you extrapolate the value of pressure, okay, pressure versus temperature, okay, at 0 degrees Celsius, okay, you can see the difference in pressure for all for different gases. For instance, we have gas number one, it gives you some pressure, but when you extrapolate, this is what we call extrapolations of the graph. Okay, that means you expand the graph towards certain point, and it should reach at this one at a very one or a very single point that is equivalent to what? Okay, so it states that okay, if the line of the graph are extended back towards the negative temperature, we find an amazing results. Okay, you can, in every case, regardless of the type of the gas, the value of the low starting pressure, the pressure extrapolates. Like I'm telling you, extrapolates, okay, to zero when the temperature is at 200 negative 273.15. Okay, because the lowest possible pressure is when pressure equals to zero, a perfect vacuum, the temperature is 2273.15 degree Celsius must be represented. It's not too, okay. 273.15 degree Celsius. That means pressure equals to zero, represent a lower bound. This is what we call absolute temperature or absolute zero. That means the temperature when pressure equals to zero is at negative 273.15 Kelvin. Sorry, point 1 negative 273.15 degrees Celsius is equivalent for when pressure is zero. Okay, you can see here, this is the point where the temperature in Celsius that the pressure now become zero. So absolute zero is used as a basis of the Kelvin temperature. So we as a researcher or as a scientist use a lot of, okay, scale in Kelvin. That's why the SI unit for temperature will be Kelvin. Okay, that means all scientists in the world, when we talk about, okay, some part of the world, maybe in Malaysia, we use as a degree Celsius, but some part of the world, maybe in the Europe or in the West, for instance, we have USA, they use a Fahrenheit. Okay, we have a Celsius. Okay, they use Fahrenheit. Okay, when we talk about temperature, okay, it doesn't fit to any value. So therefore, we need to come as a scientist. We need to come at a we need to come to the very our own scale. Well, then we use a Kelvin scale. That's why Kelvin is the SI unit for temperature. Okay, so what is equivalent to Kelvin? All right, so in 0 degree, Kelvin doesn't use scale, right? And Kelvin doesn't use degree, okay? Because at 0 Kelvin, we say when you write down Kelvin, don't put degree. The degree ni, if dah macam ni, this one is degree. Degree Celsius, ada O yang kecil tu, that is degree Celsius. Tapi kalau tengok pada Kelvin, it doesn't use degree Kelvin, no. Degree Fahrenheit, yes. Okay, there is also degree Fahrenheit, degree Celsius, but we doesn't use degree Kelvin. Okay, the Kelvin is the scale of where the pressure is zero, it equals to the temperature of negative 273.15 degrees Celsius. Okay, so that's what we call as absolute zero. The relationship between these two temperature scale given here, that Tc, which is the temperature in Celsius, and T is the Kelvin temperature. Okay. Notice that we aren't including units here only because they are so cumbersome. So we'll generally leave them off until the very end, which is the Tc equals to T, the temperature in Kelvin, minus with 273.15. So Kelvin, okay, Kelvin, uh, defined as 1 over 273.16 of temperature of the triple point of water. Okay, triple point of water. So you don't have to know about this one. Okay, but now we need to compare between Fahrenheit, Celsius, and Kelvin. So to make it easy, make sure that you put a Celsius at the middle one. Okay, don't use their diagram here because we can have some conversion of from Celsius to Fahrenheit and Celsius to Kelvin. For instance, we have 0 degree Celsius is equivalent to 273.15 Kelvin. Okay, so if you want to get any Celsius to Kelvin, you just add with 273.15. Okay, but if you want to convert it from Celsius to Fahrenheit, then you can use this equation. 9 over 5 times the degree in Celsius plus 32, so you get the temperature in Fahrenheit. So that's the how to convert from Fahrenheit to Celsius. Okay, so we can use that value, which is 5 over 9, the Fahrenheit temperature in Fahrenheit minus 32, so you get it temperature in Celsius. So it is quite easy to understand that. Okay, at the ice point of the Celsius is at 0 degree Celsius, which is equivalent to 32 degree Fahrenheit and also equivalent to 273.15 Kelvin. Okay, and then if you can look at the steam point of the water, okay, steam point at 100 degree Celsius, 212 degree Fahrenheit, and 373.15 Kelvin without degree. Okay, so how can we consider that? Okay, you put, okay, to make it easy for you. Okay, make if you want to get the conversions correctly, so you put the temperature in Celsius in the middle, and then on side by side, okay, you can measure it. Okay, you can put TC or TKF. Okay, like the one I did, I should write it down here. Okay, so we write down TC first. Okay, TC. So you can go to this side as the temperature, the absolute temperature, and the equal to this side to temperature in Fahrenheit. Okay, make the temperature to Kelvin. If you want to calculate temperature from Fahrenheit to Kelvin, for instance, you can go to Celsius first and then you convert it to Kelvin. Okay, so if you want to get from Kelvin to Fahrenheit, you can measure it, you can convert it to Celsius, and then this from Celsius it goes to Fahrenheit. So make sure you put the temperature in Celsius in the middle. Now let's go to the next slide. Okay, the examples of it. The temperature gradient between the skin and the air is regulated. This time now. Okay, regulated by a cutaneous blood flow. So convert these temperatures, okay, from um, 72 degree Fahrenheit to 84. So 72 you get 22.6, 22.2, and then 84 you get 28.9, and then the difference in the temperature, which is 6.7. Okay, so this is just a normal example. So I don't want to go that. You can go very fast here and also very fast here. Okay, you can do on your own for this part. Okay, because I want to highlight the thermal expansion of solids and liquids. Okay, as usual, the thermal expansion is what we call is you give some heat to the solids and liquid. Okay, what will happen to the equations? All right. So if there is a thermal expansion of an object, okay, so you may use this delta L equivalent to alpha L naught delta T. So this is the equation, the thermal expansion. Okay, the thermal expansion, that means delta L is the change of L and L naught. That means this is the final L and this one is the L naught, or should I say original length, time equivalent to A, okay, alpha. Alpha is the coefficients of linear expansion, okay, and of course delta T, which is T minus T naught. That means change in temperature. Okay, so if the thermal expansion of the object is small, then we can approximate the change in any dimension as the proportional of the temperature change. So if there is a change in temperature, so you can see a difference in delta L or difference in L. So this is the value for alpha, the coefficients of linear expansion is given in the list, the table. Which is at a certain material, and you can see this is a material and this is the value of alpha. So that's to this part. Okay, we have, okay, on this side, on this side we have some materials that is considered to be metal. Okay, and this one is the fluid. Okay, this one is solid, this one is fluid. Okay, and always refer to the table. Okay, so let's go to the examples of the linear expansion, for instance, all right? So a steel railroad track has a length of 30 meters when the temperature is zero. Okay, so at zero in 30 meters, what is this on a hot day when the temperature rises to 40 degrees Celsius? Okay, so rises to 40 degrees Celsius, so you may find that the delta L calculated by alpha L naught delta T. Alpha, you can refer to the table. Okay, this is the L naught, which is 30, and then delta T is 40 minus by 40 minus 0. So delta T. So you will get 0.0313, and then of course the L, the final uh, the final length, okay, the length is equivalent, it have reached, this one is delta L, delta S is the change in L, and then of course you add to the original length, which is 30, so it will get you 30.013. Okay, so this is when you apply a thermal to the to some solids, okay, or some liquid. And then suppose the track is nailed down so that it can expand. What stress results in the track due to temperature change? So from the previous chapter, which is we learned about a young, so when you apply some young modulus of the steel, and then you get to delta L. So this is delta L, and this is the L naught. So you can find that the stress is equivalent to 8.7 10 power of 7 Pascal. Okay, okay, kita cepat-cepat je. Now we go to the thermal expansion of solid and liquids untuk bahagian kedua, which is we call it as area expansion. Okay, area expansion. So the thermal expansion of a homogeneous metal washer, you can think of a thermal expansion of a magnification photographic enlargement. Kita tengok kepada this side. Okay, tengok dekat sini. Okay, as the washer is heated, all dimension increase, including the radius of the hole. Okay, of radius of the hole. Okay, you can see here when you apply some heat, okay, to the washer, and then it increase at all. Okay, meaning that the area, the temperature, and also this side also increase. Okay, so we look into the situation. As the temperature is increased, the length of each side increase. So the new area is given by these equations, right? So when you apply one side, okay, when you apply to one side, it expand only at one side. But when you apply to the whole area, so it's actually the area have been significantly, okay, increase or expand. The expense of L, that means you add another L from this side. Okay, let's say you have L naught, okay, and they have another L, so you can put it in the coefficients of area expansion, like the one that we calculate here, which is A equivalent to A naught is equivalent to L naught square. but A in the L square. So you put everything in the previous slide, which is at L not plus the A alpha L not delta T, and you multiply, you square it, so you will get to the value where you can define as delta A is equivalent to gamma A not delta T. Okay, another coefficients of area expansion. Okay, to be precise, coefficients of area expansion. How can we use that? Now we need to look into the situations. Okay, a circular copper ring, okay, copper ring atau cincin at 20 degrees Celsius has a hole with an area of this value. Okay, this is the area. Okay, you need to change it to meter square, or maybe you can just be it that way, like the one they did here. But because we can cancel out centimeter square and centimeter square, so you can also get the value. Okay, what minimum temperature must it have so that it can be slid onto a steel metal rod having a cross-sectional area of 10 centimeter square? Okay, 10 centimeters square. Suppose the ring and the rod are heated simultaneously. What minimum change in the temperature of both will allow the ring to be slid onto the end of the rod? Okay, so in the end, we need to find, okay, this is the delta A, which is the cross-sectional area, okay, by you, meaning that 10 minus with 9.98, so that is the change of A, okay, change of A, 10 minus 9.98. And the lambda is given by the copper, okay, the gamma area or the length which is used by 2 times alpha, 2 times alpha, this one, as the gamma, which is 34 times 10 power of negative 6, times with the original area, and times with delta t. The delta t here, okay, have calculated at 98, 59 degrees Celsius, sorry, 59 degrees Celsius calculated, okay, based on the terms. Okay, because now we want to calculate based on the value, right? So in the end, the last question will be, suppose the ring and the rod are heated simultaneously, what minimum change in temperature of both will allow the ring to be slid onto the end of the rod? Okay, so we might use this equation. Okay, just use this equation, but you need to expand it. Okay, so don't bother about some mathematical here, but just focusing on the delta E equivalent to gamma alpha naught delta T to get the value. Okay, so you can do the some mathematics here, but don't bother much about this mathematical uh, situation. Okay, the mathematical set. Okay, you can always do that part, no problems, because it's just a matter of a value that very significantly, very small change of it. Okay. All right, so we go to the next part, which is the thermal expansion for solid and liquids, but specific for a volume expansion. Okay, volume expansion. Now we have covered the linear, okay, the linear, only the alpha. Then of course, when alpha, when you have the area, it should be 2 times alpha, okay, 2 times alpha, which means we use gamma alpha in the previous slide or in the previous slides, okay. So this okay shows some increase in volume of an object accompanying a change in temperature, okay, and all the average coefficients of linear and also volume expansion in the degree Celsius or degree Celsius -1. That means the unit is degree Celsius -1. Okay, so can see here the average volume or the coefficients of the volume expansion at the very end of the material at the maybe in the fluids, in the regions of fluid. We use that as beta or 3 alpha. Look at the words they use. Beta or 3 alpha. Delta V equals to beta. V naught delta t, or we can use 3 times alpha. Remember, alpha is specific for linear expansion, and 2 alpha is the expansion for area. Okay, that means area. And then 3 times alpha is an expansion for volume. But that is for because okay, consider this kalau kita panaskan, okay, let's say kita panaskan air yang diletakkan di dalam metal ataupun bekas aluminium ke copper ke, so you can see that way. Kita panaskan dua-dua sekali, okay, maksudnya kita panaskan, actually kita panaskan air, tapi air akan expand. Okay, air itu letak dalam ini. Okay, should be in the air akan expand, maksudnya beta akan expand, dan pada masa yang sama bekas yang mengandungi air itu pun akan expand juga. Okay, so maksudnya dua-dua sekali akan expand. Air pun expand, bekas tu pun akan expand. So sebab itulah ada 3 alpha and also beta. And beta we use for fluids and alpha we use for metal. Okay, so let's look into the examples. Okay. Okay, so estimate the fractional change in the volumes of Earth oceans due to an average temperature change of 1 degree Celsius. Okay, so we use the delta V equivalent to beta V naught delta T. So you bring V naught to this side, and we left with the beta, which is use a seawater, the oceans. Okay, use a beta, and then you multiply with the delta t, because 1 and 0, so 1 minus 0, so you may get uh, some fractional change, okay? Fractional change, which is 2 times 10 power of negative 4. And then lastly, use the fact that the average depth of the ocean is 4,000 meters to estimate the change in depth. Note that the coefficients of volume expansion for the water is this value. Okay, so that's why we can use that value. Right, in part B, we use a delta L, okay, because as I can see, okay, this is the average depth of the ocean as 4,000. So you may see that the estimation of the change in depth, and the change in depth is considered to be in the kind of volume. So volume times the depth, so you get volume, sorry, area times the depth, you can get volume. So that's why in here we have alpha L naught delta T. So that alpha, okay, so we can change it to beta over 3, because we have beta. Beta divided by 3. Okay, because the 3 alpha is equivalent to beta. Okay, remember 3 alpha is equivalent to 1 beta, because right now we doesn't have alpha. Okay, but we can use a beta. So beta divided by 3 times the L naught times delta T, where the L naught should be the 4,000 meters and temperature is 1 degree Celsius. So you will get 0.3 meters. Okay, and then lastly, I don't know, oh, it's already last. Okay, so that is the only, okay, the 3 expansion for thermal. If by considering you have linear, okay, you have area expansion, and lastly you have a volume expansion. Okay, alpha, 2 alpha, 3 alpha, and 3 alpha also have a beta. Okay, as I said to you, volume dia boleh jadi dua, sama ada dia akan naik, dia apa, area alpha akan kali 3, ataupun volume of the fluid akan expand juga bersama-sama. Okay, when you give a thermal expansion. Okay, so with that, kita settle untuk chapter 10. Okay, the stability sampai thermal expansion. Okay, so as for now, ada soalan ke? Tanpa semua dah atur dah. Okay, sekejap saya nak share ni. Saya nak share link kehadiran ya. Ya, nanti boleh masing-masing isi link kehadiran dalam Google Form yang saya bagi tu. So, boleh isi ya. And then saya ada juga uh, YouTube. Sekejap ya. Saya bagi link pada YouTube playlist. Okay, playlist tu ialah last year ataupun um, sebelum COVID atau masa COVID saya punya lecture-lecture masa COVID. Masa tu kan banyak buat kelas online, so awak boleh refer kepada YouTube channel tu lah. Saya ada uploadkan ke situ. So dalam tu juga ada tutorial-tutorial lepas-lepas, perbincangan tutorial lepas-lepas, boleh tengok juga Okay, sesajalah bagi. Bolehlah, feel free tu. Tapi dia bukan um, yang baru bukan saya punya video yang baru, tapi itu video lama. So kalau ada kesalahan tu, feel free to comment ataupun boleh bagi tahu saya sendiri. Okay, sebab kadang-kadang kita mengajar lama takut ada yang tersalah info, but so far adalah. So feel free to comment, no problem. Wah, laju attendance dah 60 lah, 65 laju. Please. Okay, alhamdulillah. So kita dah settle untuk chapter 9 and chapter 10 dan okay, tomorrow tak ada lecture Please